Okay, to run through what we did yesterday, or what you were investigating yesterday, we're going to investigate what happens when we do transformations on this graph. I'm going to do it 2 times. I'm going to do it once with a linear function and show you that all linear functions are actually a transformation of the line y equals x, apart from x equals 0, x equals something and y equals something, just a single value. So horizontal and vertical lines aren't included, but all sloping lines are some combination of transformations of this straight line. So the first thing we're going to look at is the conclusion of what happens when we do f of x plus some number. I'll just scale this so it fits. F of x, yeah. There's my function f of x, the green one. Remember that in future. So we're doing what happens when I do f of x plus some number a. Now I can put it in. Let's put in f of x plus a. It's 1. What's happened? It's moved up 1, moved up 2, moved up 3. So the f of x plus a number. If you look at this, some people think it moves left. We'll check that in a minute with a different graph and you'll see that it is a translation in the y direction by whatever a is. And if I put y over here to see the graph, there's a reason I'm doing the y over there. The second one is let's edit it. So we just keep one graph. What happens when I add the number inside? So that's my f of x again. If I add the number inside, it moves to the right. So this looks like it's moving up. It looks the same at the moment, but you should recognize y equals x plus 1. So I'll put a little example in. You should recognize that as being x plus a as a single function. The second one does the same thing. It gives me an x plus a. So it's you should recognize that it moves it up by 1 from previous experience with graphs. So f of x plus a number in here, and I keep calling d, and that should be d. So let's play with that number a few times. 4 moves it up, so it's moved up to 4, and f of x minus 3 moves the line down so it goes through minus 3. So don't worry about this intersection at the moment. We'll have a look at another function in a moment. What about the multipliers then? So I'm going to do y equals fx times some number. And I'll put it on the outside of the capital just to show something that it's not a normal value. So we've got rfx. If I say times 2, y equals 2x, you should recognize it's stretched it in the y direction. This point's moved to that one, this point moves to that one. Okay, so that is a y stretch. And because of what happens when I do a minus 1 in here, which is a reflection in the x-axis, that's a reflection in the x-axis, we say this is perpendicular to the x. And then by a scale factor of a. It's only a stretch, it's not an enlargement, because both directions don't get hit at the same time. Do the same thing again for, put another value in, so if I do a 0.5, it says scale in the y direction of a half. Okay, perpendicular to the x-axis or a y stretch. And the last one is the multiply in the top. It's to put the value inside the x, the function. So if we put 2 on the inside, again this is taken this point and stretched it that way by a half. Now I know that's hard to see with linear functions, So we're going to go through this again, or perpendicular to y, and this is a factor. Sorry, this one we forgot to write. It was a translation, and it's left, so it goes the wrong way. I'm going to leave this as a, so it's minus a, 0. And this time, what's happened in the x direction is we've halved the values, or 1 over a. Everything's got squished closer to the y-axis. Okay, so that's what can happen with those. Let's change the function and just run through and check and see if that's the same thing that happens with a quadratic. So we've got a quadratic curve. Hopefully this time you'll understand why some of these are in the directions shown. And this you should have realised from yesterday's experiments. So if I take fx and add a number to it, we've translated the graph upwards. Yep, so with x squared, that's worked. Let's try doing a number inside the bracket. So there's my 0. Let's watch what happens to that apex, the bottom point. You want to see where it moves to. So if I add 3 to this, it's moved it minus 3. It's gone left 3 places. There's no other thing this could have been. Before we thought it might be the same as the previous one, but by using a quadratic, we've actually seen it move to the left. So it moves in the opposite direction. Do the multiplying ones. So if I take the x squared graph and I multiply by 0.5, it's going to take all the y points and halve them. So all the y points move down. Some people think of it as moving the x direction, but we saw that linear. We'll do one cubic in a minute, and I'll show you that these can't move horizontally in the same way. And so this is a half in that direction. If I do a 2 in the y direction, everything gets steeper. All the y values multiplied by 2. All the y values are multiplied by 2. And what happens when we do the stretch with 2x? 2x, it's stretched it in this way by 2. Now notice, if you thought that this was going to, is the same as doubling in the y direction, that would have taken it to here. If you've taken it, it's actually gone 4 times as big in that direction, because we've actually got 2 times itself squared. So there is a sort of equivalent y squaring, but it goes with the function. So in terms of this function, it goes half the distance across. Let's do one other function, and this is a weird one, but it does help with some of the others. Sin x, and make our function normal, first of all. Hopefully you recognise now if I add 1, it should move it up. Everything's moved up, it's not moved left or right. If I add 1 to the values, now notice the scale on here, it's not 360 degrees, it's using a different form of measurement. But what we're expecting to happen now, according to this, we are expecting that point to move back 1 place. So if the green point has moved back 1 place. Yes, that worked. Multiply on the other side by 2. We're expecting everything to get twice as far away as it did before. Now twice as far. This point twice as far. This point twice as far. If I do 4 times, this point's going to get 4 times as far away. This point's going to get 4 times as far away. Okay. And if we do the numbers on the inside, and there's no way it could be a transfer this across now, because this top point doesn't transfer across, it's the maximum point stays in the line. So if I do now a 2 inside, it has to have moved in the x direction because all these high points and all these low points have moved to the left. So between those three graphs, hopefully I've shown you all these transformations are working correctly. If you put negatives in, you're getting the flips. And now I'd like you to have a go at exercise 26.3, and I'll put into the lesson the questions that need to be answered. Have a go at the whole of question 1 now, and then start working on the graphs and the other functions going through. So they do talk about some things like sine of x and other things. I'll probably ask you to skip those until we've done some more stuff with sine.